Welcome to the extra live session of Quantum Chemistry of Atom and Molecules, NPTEL course. I am Marco Provo. I am a PMRF at the Department of the Chemistry at IIT Bombay. So I am taking this extra live session so that I can clear the doubts and solve some numerical problems of this course related to the quantum chemistry. I try to follow the lectures, lecture by lecture, so that we can discuss those specific problems that can come into some assignments or something. Uh, so today we'll going to discuss some of the MOT problems, molecular orbital theory problems. But before that, we'll go back to the last class and where we have ended and try to come try to come to the MOT and solve those problems um, by that step by step. So you already know that these sessions will be recorded and available in the YouTube, and it can be available in the YouTube, and those who are taking the NPTEL course, they have these links and links of the notes and the slides to access in the future. So in the last class, what we have done is that we have done some problems from the variational methods, where we have solved the problems of this, like one problem like the energy, obtaining the energy of the ground state of a SHO, simple harmonic oscillator. And the trial wave function is given, and the thing is we need to see that what is the epsilon or functional that is coming as a by putting the variational method, means the energy, and that energy will always be greater than or equals to the original energy. So for that, what you need to do, that you need to first let me change my color maybe. So you always need to find this energy, and then you need to do that, find this energy. And second part will be, if you need to see, change your variational parameters to see where the your slope of this functional or this calculated value of energy is coming to be zero. At that point it has some minimum or the maximum value. Most of the, you can put the values and check if it is coming as maximum minimum, because the slope is zero there, right? So by doing that, you can find the energy as well as the wave functions also. And from variational param method, we have understood two things, that firstly, that the energy could be exactly similar to that of your original energy, or it could be higher. That is one. Two is, for mathematical point of view or numerical point of view, there will be a lot of calculation, lengthy integration. You need to be very patient about it. Just like in the previous day, what I have done for 40 minutes, I have done these actually, derivation. This is the correct one, but I have solved maybe this part. I have solved for this derivation. I had some mistake, and that mistake carried out for the next 30 minutes or 40 minutes, and so, and I to have done the calculation and got wrong answer. uh, but as it is I need to prove this energy, I at the end I get that my answer is coming wrong. So I again go back, check where I have done the mistakes, and I have again do the integration, a very lengthy integration. So you need to be very patient about it. But if you do that step by step, you don't try to jump any steps, then eventually you will get the correct answer. And I have given one problem, so that you can solve it by yourself from hydrogen. I have solved two problems from the SHO. I have kept this for the hydrogen atom. Similar way you need to do the normalization and the uh, uh, get the energy value, calculate value of energy, and check what is d by d. Here alpha, your variational parameter, make it to 0, get the value of alpha, and play along. So actually from variational theorem onwards, from variational theorem onwards, actually there comes the first part that you can say variational method. Then in the class it is discussed that your uh, valence bond theory, right? VBT. So in VBT, actually what you have seen that when two nuclei are far apart, two orbitals, you can say two hydrogen orbitals, suppose. So they are far apart, A and B. When they are very far apart, R is equals to infinity, then you are writing you can write the VBT, psi VBT overall for H2 actually. Suppose we are doing for H2, this is 1s, this is another 1s, suppose this is 1s A, this is 1s B, so you can write your thing as 1s A 1, your first electron is 1a and second electron is in 1s B, right? Because it is far apart, but when they are close, right, like this, then your psi VBT becomes your Hitler-London equation, right? This is known as Hitler. So that is actually C1 psi 1 plus C2 psi 2, where your psi 1 is actually, now it will be a linear combination that the first case is that your first electron is 1a and the second electron is in B nuclei attached to in that atom, B atom. And another case, as it is indistinguishable now it is actually, it is something like your another electron is in the second electron in A atom and the first electron is in uh, this atom, B atom. Now you can't distinguish, and based on that, that VBT has Sir has taught the VBT, the valence bond theory, and you got the energies, values of the energies. You got introduced to different integrals like Coulomb integral, that is J, exchange integral, that is K, right? And you got the values of you got the idea, right, that what the energy curve of a singlet, and I should not say at, actually this has been already taught, so I can say how the energy curve of the singlet and triplet looks like, right? So from there you have got the idea for hydrogen atom, that if this is the 0 and this is the energy goes like this, then this is going to be your singlet, right? And this is going to be your triplet, that is A minus and A plus, and this comes from a positive. So actually what is actually you are going to do, if you think out only the plus right now, maybe let me erase minus and let me write only the plus, and then from here on what you are actually doing that, so this is your psi 1, let me write it in this format, maybe written mistake here, psi 2. And then actually what you have already done, that you have varied, you have checked the different. So once you have done d psi VBT, like separate del psi VBT of del C1, you make it 0, del psi VBT with del C2, then make it 0, right? Sorry, I have made one mistake here. So you try to get the energies of this. Let me go to the Google Meet once. Has someone joined, or No, stay in the call. Where is my cursor? Okay. So from here you need to get the energy, right? You need to get the energy in form of, as variational theorem already we have discussed here, this energy is going to be, you get the energy in form of, maybe let me write E, um, in form of psi BBT, your Hamiltonian for this, and then again your psi BBT. If you do this and you put this C1 psi1 plus C2 psi2, you are going to see that you are going to see that whatever energy you are getting, that you again get a derivative with respect to your variational parameters are here C1 and C2, and you have to remember that your E actually depends on C1 C2 as well as the psi, right? As it is dependent on psi, it is means the psi can vary based on the C1 and C2, the C1 and psi, that can vary, and as they can vary, you varying them and you are trying to see at what value of C or at what value of C2 it could be minimum a maximum energy according to the variational parameters, and from there you can watch the lectures. I'm not going to the deep. You can see that how your energy profiles look going to look like, and what are the other calculations. Okay, now from here the main problem of VVT was that obviously you are getting some sense of the triplet, triplet being the triplet state and singlet state, but it is very problematic for multi-electronic problems, and it can't VVT can't really talk about the delocalization. Then comes the picture, then we can discuss that. Then after VVT, means with VVT, I should write 2, maybe 2b, and this is 2a. With VVT, the concept comes hybridization, right? And in hybridization, you have to remember one thing, that it is whatever orbitals we are generating, that is generating in only one atom. Hybrid. So this is a common mistake. I also have done the mistake. Orbitals of one atom, and those hybrid orbitals are going to make are going to take part in bonding with the other atoms. So hybrid orbitals will be formed in one atom, and then they are going to form the bonds. Okay, today, and you already know that there could be two types of hybrid orbital. One is equivalent, and another could be non-equivalent. So equivalent hybrid orbital means your suppose your sp orbital or sp2 sp3. In these cases, when sir has discussed about the problems, I think for sp, I think sir has discussed maybe acetylene, and for sp2, who maybe sir has discussed bf3, boron trifluoride, and for sp3 I guess sir has discussed the methane. In those cases, what is happening, all the hybrid orbitals of carbon, so there the main atom was carbon, so hybrid orbitals of carbon was generated in the examples I am saying, like in acetylene, or in case of BF3, is the central atom is boron, and so the hybrid orbitals on boron, and then these hybrid orbitals uh, have same energy, or they are energetically degenerate, right? And one more thing, in all the hybrid orbitals, total s character, total p character are same. Suppose what I'm trying to say for BF3, I'll start from the beginning. That BF3, the hybrid orbitals are, so this is sp2, right? So sp2, so hybrid orbitals of boron is generated, are generated, right? And then they are going to make bonds with fluorine, right? Fluorine, uh, that depends, because then boron, and you have to see that which orbital of boron, fluorine is going to make bond with that, but that let it be the another case. But here, if you see the hybrid orbitals, then hybrid orbitals are generated only on the central atom, that is boron, right? And three boron, so what are the so if you, so now you can think of a BF3 is a planar molecule, right? So it would look like something like this. Suppose so 2s orbital of boron and 2p orbitals are valence, as it is coming from the valence bond. So the valence orbital, what is the valence orbital? 2p 2s, this second, right, second row. So 2p and 2s are going to take part in the hybridization, and upon that, if you think of that, their z axis is coming towards you out of the plane, means out of the screen, then you can see that the pz orbital is not going to take part, right, in bonding. So by that way, px and py, they are going to take part, and s orbital obviously is going to take part, as it is spherically symmetric, right? So that is going to take part. So you can see 1s and 2p, means sorry, 2 what I am trying to say, that uh, 1s orbital, that is the 2s orbital, and 2p orbital, that is 2px or py, if I consider, so that is up to me, that if I consider that bf to be along z axis, then pz is going to take part in the bonding. But if I say that my z axis is coming out of the plane, out of the plane of the screen, then suppose this is y and this is x, right, and towards me is z, right, towards us. um, how to show this, maybe that vector point, so it is coming towards us, right? So that arrow, it is coming to you. So if z axis is towards us, then 2pz is not going to take part in the hybridization, only px and py have some contribution there. And here one s, one of the s, and two p orbitals are going to take part, and that is why three hybrid orbitals, three sp2 hybrid orbitals are going to generate. So these are all equivalent hybrid orbitals, but there is something also as non-equivalent hybrid orbitals, like in case of H2, as sir has discussed. So I am actually going to solve the problem of the sp2 for the water, and from here we'll get some idea of the non-equivalent hybrid orbital. I know sir has discussed it already, but let me go step by step, so that uh, we'll get some idea about it. So the question says, for water, it is experimentally determined that the hydrogen oxygen hydrogen bond angle is 104.5 degree. Okay, this bond. This is hydrogen, oxygen, this is oxygen, and this is hydrogen. So this bond is 104.5 degree. Determine the coefficient of the atomic orbitals of oxygen, so that participate in hybridization. So the first goal would be that find out the hybrid orbitals on oxygen or off oxygen, you can say. So if I think of the electronic configuration, that is maybe the valence part, that is 2s2 1s2, 2s2 oxygen is 8, right? So 1s2, 2s2 to be 4, right? Something like that. And so 2s and 2p are going to take part in the hybrid orbitals. That is what I am saying. Okay. So the valence bond. So maybe suppose I am writing the first. Uh, okay. Here let me discuss two more things. See, schematic from the schematic it is said that the lone pairs is in the XZ. So this is another. So right now our let us consider from this image we can see that hydrogen, oxygen and hydrogen to be in the YZ plane. Okay. So X axis has no role to play here, and the angle between this is 104.5. Okay, so I'll write hybrid orbitals on oxygen. It is some always we do it for the central atom. So that is going to, so it will have some, obviously it is going to have a normalization constant that will come later, but it will have some contribution from the oxygen 1s. So that is why I am writing oxygen here. So sorry, 2s orbital, right? 2s orbital, it will have some contribution, let us write C1, right? And then it will have some contribution from the px orbital, px, py and 2px plus 2py plus 2pz, right? It should have some contribution from this, but you will see that as x-axis is orthogonal or 90 degree to yz plane, so it would not have any contribution on the hybrid orbitals. Okay, so your contribution of 2px is going to be 0. Okay, ultimately the whole thing is going to be 0, but 2py and 2pz, 2py and 2pz has some contribution. So that is, let us write C2 contribution, I should say coefficient. Okay, the contribution is actually contribution is actually mod of the coefficient, mod coefficient square, right? Coefficient square, that is square of the modulus of the coefficient, that is your contribution. I am here writing the C1, C2, C3 are the coefficient of these atomic orbitals in formation of your hybrid orbital on oxygen. What would be, so see, there are two hybrid orbitals on oxygen, right? And those two, so bonding hybrid orbitals, those are going to make bonds with the 1s of the hydrogen. So I will say that this is your H1 and this is your H2, and it is your 1s of hydrogen that is going to make bond with these hybrid orbitals. And obviously there are two lone pair orbitals, hybrid orbitals on oxygen, that we are going to discuss anyway, but let us first discuss the bonding ones. So these are two of your bonding hybrid orbitals. Okay, so this is the H2O, H2O, the second hybrid orbital on oxygen. So it will also have a similar normalization constant, right? Because they are equivalent, I am saying, and these bonding hybrid orbitals are equivalent to each other, but non-equivalent to the no, lone pairs, right? Lone means the hybrid orbitals related to the lone pair hybrid orbitals. So see, as it is 2s, 2s should have equal contribution, right, to the second hybrid orbital as well, as because it has no direction. It is symmetric, spherically symmetric. Again, your 2px is not going to have any uh, coefficient, right, px orbital, but your it is going to have c4 2py and c5 from 2pz. Now we need to understand what could be the coefficient c2, c3, c4 and c5 are. Okay, now as there is an angle is given, suppose the angle between this is 2 theta. Let us suppose this is 2 theta. This 2 theta is 104.5 degrees. So this is your H1, this is oxygen, and this is H2, and this is your 2 theta. Okay, and this is your z axis. So ultimately, and this is your y axis. So let me change the color. So this is your theta. So contribution on the py orbital would be on H2, suppose, uh, would be uh, sine, or you can say this is uh, cos of 90 minus theta. That is going to your coefficient, right? And what would be the y axis? This is minus y, right? So the contribution of y axis on H1 is going to be minus cos 90 minus theta, and this is nothing but sine theta, right? And this is nothing but minus sine theta. Okay, so we are discussing about C2 and uh, C4. So what we understood that your coefficient of y-axis 2py on H2, that is your C4 is sine theta and C2 is minus sine theta. So, and what about the z-axis? Z-axis has directly cos theta, and this is also the same, the plus. So this is minus z is along this, and it is plus z. So it is also going to be cos theta, right? So your C3 is going to be equals to C5, that is cos theta. But we don't know the value of C1, so we'll keep it C1, and let's see what is the new thing we have got. So H1 on oxygen is actually C1 2s. So we should not forget the normalization constant C1 2s plus C2 is your minus sine theta minus sine theta 2py. So I am not writing at psi. I have not written the 2py itself is the atomic orbital, and then C3 is nothing but cos theta, right? Cos theta 2pz. What about H2 on, again, that is your normalization constant C1 2s plus sine theta 2py plus cos theta 2pz. Wait for a bit. Let me plug in my charger, laptop charger. Yes. So now you got some idea that, and we what we know from the hybrid orbitals, that hybrid orbitals are are orthonormal. So they are normalized and orthogonal to each other. So we will take the property of orthogonality between H1 and H2 and try to see that what is the value of C1 is coming. We already know what is the theta, right? Theta is half of 104.5, that is I think 52.25 degree, and so we know the value of sine theta, cos theta, those we already know. I'm not putting the values yet. So from there we can get the value of the C1, right? So let us see that what is coming. So my cursor, using the orthogonal relationship between H1 and H2, these are the hybrid orbitals. We know that your n C1 to be x, sorry, I made a mistake. This is 2s, right? 2s. Then this is minus sine theta to py plus cos theta to pg multiplied by n c1 2s. Now for h2 it is sine theta, one coefficient of 2py, plus cos theta of 2pg is 0. And why this is orthonormal? Because it is the hybrid orbitals are on the single atom. Okay, that is why they are orthonormal. And again, the 2s orbital of the oxygen are orthonormal with the p, right? Sorry, 2s are going to be individually normalized, and 2s and 2p, if you multiply and get integrate all over the space, you are going to get 0 because they are orthonormal, right? So they are orthogonal. So as you know that n into n is into is all is, let us, as n not equals to 0, we can write that what we are going to get is c1 square 2s 2s, all the cross terms are going to be 0, so I am not writing that. So I should put this, right, d tau. So this is the relationship, plus cos square theta to pg, this is 0, not the multiply but the multiply and integrate all over the space. And we know these are normalized. I have not written the cross term because they are already 0, right? So your c1 square minus sine square theta plus cos square theta is 0, which is nothing but this is actually your cos 2 theta. Okay, so you are going to get your c minus cos 2 theta, okay, which is minus cos x 104.5 degrees. Don't forget this is in degree, and this value you are going to get as let me calculate, as 0.25 almost, and there are some in decimal. I'm not writing that part. And if you now your C1 could be square root of this, which is 0.5 plus minus 0.50. Okay, so that is one thing. What about C2 and C3? So your how does your H1 and H2 looks like? Ultimately your H. So let me also write uh, the value of sine theta is actually your sine 52.25 degrees, right? Which is sine 52.25 degrees is 0.8, or you can actually it is 0.79. Let me write 0.79, and cos, that is actually cos theta or cos 52.25 degrees is actually 0.61. Okay, so your H1 on oxygen is, let me take the plus 0.50 psi 1, sorry, uh, 2s minus sine theta 0.792 py plus 0.61 to pz. But don't forget the n is still there, and H2 on oxygen is your n, right? And then it is, I can take this as plus, then this is actually plus sine theta, right? Plus, and this is same 0.61 to pz. I can only take any one of this, plus or minus, any one. That depends, I think Sarah's discussed, right? The C1 is going to be negative or positive. One can take either negative or positive, depends on the lobes, right? Sarah's discussed that in the thing in the lecture. So I would request you to go there and check that particular lecture, because Sarah has shown the very beautiful figure to let you to for understanding purpose. I don't have that figure with me. That minor lobe, say that nucleus is going to be in the minor lobe, that is why it should be negative, but one can go with the positive also, that doesn't really matter. Ultimately we are going to deal with the contribution, and contribution is the square of the magnitude, right, of the coefficient, so that doesn't really matter much. Now we'll figure out what is the value of n, and that can be done from the now using normalization condition. Here we already got this value, integration of n 0.502s minus 0.792 py plus 0.61 to pz multiplied by n 0.502 ps 2s, sorry, plus 0.79 to py plus 0.61 to pz is 1. Okay, as it is a normalization condition, and multiplying with the volume element also, and that would lead to again the similar setup that n square is there, now multiplied by 0.50 square 2s, and the cross terms are eventually going to be 0, as you can understand. That is going to be minus n square, 0.79 square to py and minus n you can understand because this is minus and plus. So for C1 we can take only the same value. Here if it is 0.5, it has 0.5. It is plus, this is minus, this is not, because we have written at the beginning itself that your both have the equal coefficient, right? It could not be 1 plus 1 minus. So you can either have only the plus 0.5 or minus. So eventually you are going to get plus 0.50 square as contribution, right? Next is 0.61 square 2pz 2pz. These are going to be 1, right? So I'm writing this in bracket notation. I hope, or Dirac notation, you already know this thing. You are comfortable with I guess you are comfortable right now. And this is the value 0.25 we know, and then 0.79 square, that is going to be 0.62 plus 0.25, so that is 0.25 I think I have made a mistake here. I think I have made a mistake somewhere. Sin minus, yes, the mistake I am making, that I am, for a normalization condition, what I should have done, that I cannot take h1 and h2, right? I am doing that mistake here. So let me erase this part. Maybe I should have write these conditions at two places, right? So this should be your h1 into h1 d tau is 1, right? So, and for this case it was h1 h2 d tau is going to be 0. So, the mistake I have taken a I am saying normalization condition, but I was taking uh, the orthogonal condition. That is, here it should be minus, right? And vice versa, one can do with h2 d tau is equal to 1 also. But we are currently dealing with h1 into h1, so ultimately this is also plus, so this is also plus, so your n square is going to be 1 by 1 point, let me see, 0.25 plus 0.62 plus 0.37 going to 1.24, and divided by that is 0.81 actually, 806. I can write, so as I was writing at 2 decimals, so I'll write like this. So your n is going to be 0.81 is 0.89. So n is going to be your 0.89, the square root of this, right? 898, which is actually 0.9, you can say, right? So ultimately, so I'll write again in the this. So you got, so I'll multiply this 0.9 with 0.5. So maybe 0.45 2s minus 0.71. So I am multiplying n with my 0.5, 0.79 and all. 61.5455. This is my h1 and h2 would be just the signs will be different. So one can check that if 5 square plus 171 square plus 155 square is 1 or not. It is, as I have taken some uh, as there are some terms after the decimals, or I've taken something, so that's why the square of 0.45 square plus 0.71 square plus 0.55 square is coming to be 1.0091, as which you can actually think of 1, and these are normalized, and these are equivalent hybrid orbitals, equivalent bonding hybrid orbitals. Things to notice is that what is the percentage of S character, right? So the S character is 0.45 square, which is nothing but 0.2. So S character or contribution from the S is 0.45 square, which is approximately 0.20, and P character or contribution, overall P contribution, which is 0.71 square plus 0.55 square, or you can minus 1 minus 0.20, that is your 0.80, right? So it is coming to be 0.80. So it is something like, if you, it is not sp3 but something like sp4, right? That's one of the inferences you can draw from this. These H1 and H2 are hybrid orbitals that will go for the bonding case, but you are still going to have something as H3 on oxygen and H4 on oxygen, which are equivalent to each other, equivalent lone pair hybrid orbitals. And if you take H1 and H3, these are non-equivalent pair, right? Equivalent, I should write equivalent pair. Yeah, non-equivalent pairs. Sarah has already solved this, but just to show you the calculation and all, I have solved this thing here, step by step, and you can try with H3 and H4 yourself. Okay. Now from the hybridization, one wants to go to the next. In case of the valence bond theory, there are some, you can say, uh, improvement we can do in terms of, we can't really explain delocalization and delocalization and um, the excited state energies. You somewhat get for hydrogen H2, you get something fast, the triplet state, the idea of triplet state you are getting, but for the other higher excited state you are not going to get the idea from the valence bond theory. That is why that MOT comes into the picture, molecular orbital theory, and your molecular orbitals are approximated like they are, again, the linear combination of atomic orbitals, LCAO model, or approximation, linear combination of atomic orbitals, where these atomic orbitals have equivalent energy and symmetry. So that two considerations have to be there, that they have to be symmetrically matched and energetically close. Energy may not be exactly same, but they should be close. In case of homonuclear diatomic molecules, the atomic orbitals which are similar energy, same energy and same symmetry, they are going to form the bond, but there are going to be cases in case of heteronuclear diatomic molecules or polyatomic molecules where that similar energy consideration and symmetry consideration is going to play a crucial role. Okay, so with that we are going to solve some MOT problems. May not be exactly numerical, some of them are numerical, but some of the questions. So these questions are from, again, from that our department offers a physical chemistry first year course in quantum named as CH107 physical chemistry. Sometime currently it is running as CH111, and the questions are prepared by the faculty members and TAs of Department of Chemistry. I acknowledge them so that I can share these questions with you and the solutions with you. But the questions are actually prepared by the faculty members and the TAs. So I acknowledge them so that I can to let me share these questions with you. Okay. So one of the questions was the hybrid orbital question, and the next question comes in that assignment. Particular assignment is now the using the linear combination of atomic molecular orbitals. So I'm not going into the theory of the molecular orbital, but while solving this problem, we'll have fair understanding of that. And as Sir has, Professor Datta has already taught in the lecture, so it will not be much of a problem. So the first question is qualitatively plot the overlap integral SAB as a function of internuclear distance RAB for the following linear combination of atomic molecule orbitals, MOs, molecular orbitals below. First, we need to show them the overlap integral SAB. We need to plot it against the internuclear distance RAB, and we need to also write the molecular orbitals for bonding and anti-bonding for each. We have to draw the MO pictures, molecular orbitals, and with appropriate signs and assign their symmetry, whether these are Girard or Ungerard, G or U. So start from P. So let me write, this is 1, this is 2, this is 3, and this is 4. Interestingly, see, these are P, 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 D, D, D. These are also D, but here they are coming from, these are on the same plane, but these are not in the same plane. This is actually known as delta bonding of d orbitals. These are normal side-on overlap, you can say, side on, right? Now for the first case, how the MO will look like, first let us see. So the all positive, positive, negative, negative. So the MO will look like a big positive and a big negative. There are two nucleus. So how is it? What is the symmetry? So the symmetry is Ungerard, U. Okay. So we have, and this is the bonding, and so psi BMO, bonding molecular orbital, is C1 P plus C2P and anti-bonding ABMO molecular orbital is will have the same contribution, right, or coefficient, C1P minus C2P. Okay. Now how the overlap integral will look like? So this is your internuclear distance RAB, and this is your overlap integral. See, when the distance between two are 0, then they are perfectly overlapped, and at that position the overlap integral is maximum. Okay, suppose this is the maximum and this is RAB is equal to 0. Now when their RAB is getting increased, means the internuclear distance is getting higher, then the overlap is going to be smaller and smaller and smaller, and that will decrease. So actually it will decrease like in a exponential format, like this. Okay, so at infinite internuclear distance, the overlap is going to be 0, right? And this is how your overlap integral is look like for PP, side-on interaction. Now we are going for PD in the next one. So I'll draw the, so this is your P, and this is your d orbital, right? Now they are, if they form a molecular orbital, bonding molecular orbital, again psi BMO is maybe C3P plus C4D, and anti-bonding would have been C3P minus C4D. We are not specifying which D and which P are these. And now the BMO would have been look like something like this, right? They are not to the scale obviously, but this is how it would look like. Two of these lobes are going to form this uh, plus and this minus, big plus and this minus, and they are going to stay uh, like this. So this is your bonding molecular orbital. I'm not drawing the anti-bonding orbital, that you can do it yourself, but how does the ASAB overlap integral look like for this MO? So this is your internuclear distance, and this is your overlap integral between A and B. A and B means here P and D, that is two different orbitals. So see, when the internuclear distance is 0, means two nucleus is top of each other, then how it looks like? Let me draw it for you. So I will draw this first, D first. So this is minus, this is plus, and now in between plus and minus. So you can clearly see that the overlap is going to, and if you integrate, see, plus 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 minus 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 plus minus. So eventually you can say that the it will at 0 distance, it will start from 0. Okay, so at 0 it is 0, and then when it will go to some distance, so your p orbital stays it in place. Okay, and this is the current position what I am trying to draw. Plus minus minus plus, at this position they are going to have some positive means overlap, right, at this distance. So it will increase, and then there comes a position they are very far apart. I should have drawn it with the different color. And then at very RAB is very high, then your overlap is going to decrease. So your SAB will increase at some point, and then it will decrease, right? This is how it will look like. Then your third is two d orbitals are there, right? Side on it. So plus, minus, minus, plus, another d I will draw in a different color. I guess it is kept like that, plus. Actually the signs are different in that case, so I'll erase the signs of these and I'll try to cope up with the same plus 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 minus 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 plus plus minus. So these are kept as minus plus plus minus. So this is one of the D, but you can say this is minus D, right? D like this, and this is another D. So when the so I'm not going into the BMO and anti-bonding. Acha, I'll draw at least this part, that how it will look like, plus minus, and here it is. Acha, so we have not discussed about this. So this is also going to be how, what is going to be the symmetry of the second thing, right? What would be the second symmetry of P when P and D mix with each other? That is going to be G or Girard, right? Because they are symmetric in some nature. But in this case also, they are going to be, I should have drawn it in different color. So here it is minus, it is plus. There are nodes, right? These are nodes. Here is also some nodes are there, right? So you can see that this is going to be Ungerad, huh? And how the SAB is going to look like for this particular case, with internuclear distance increasing. See, when the distance is they are just top of each other, means when the internuclear distance is 0, then you can see actually the overlap is anti-bonding type, minus on plus. So they are highly, the overlap integral will be negative. They are repelling each other. I mean the overlap is not good, so overlap is negative. But when they are at this equivalent distance, then this is going to happen. So from negative it will come to positive and reach a maximum value, and then when it is going to be infinitely distance, or the distance will be very far, then it is again going to come down. So the plot will look like, it will start from negative, it will come to a positive, and then again it is going to be something like this. Let me redraw it because I messed up it. So maybe I can use negative. So it will start from here, then it will increase at some point, then again it is decrease. Okay, it will look something like this. Suppose this is the zeroth line. Okay, 0 for both is, so at 0 internuclear distance, it is, the overlap is going to be negative because they are not overlapped good, but with particular distance the overlap will be maximum, and then it will decrease and it will become 0 at infinite distance. We stay in the call. Okay, and we're left with another one, that is your fourth one, and drawing it to be a little difficult. Plus and another is same. See, this is plus minus minus plus. So they are not coming side on, but you can say mm, mm, what is different. This lobe is coming such a way that it will interact with this is coming such a way, this is interact with this is coming in a such a way, this is interact with this, and same. So as you can see, when the internuclear distance is 0, then plus is overlapping very well with plus, minus is overlapping with these are phases. You can change the size accordingly you, but the phase, what I am trying to say, they are overlapped very well when the nucleus internuclear distance is 0, and when you go further, it will decrease. So it will similarly it will look like for, I think if you remember, the PP, right, in that case. So this is RAB, this is SAB. So it will start from maximum value and it will become 0 at infinite distance. So at this distance, I hope you got the idea. So this is known as delta bonding, and the other kind of bonding will lead to your pi orbitals, right, because they are side on. So, and what kind of, obviously this is going to be, the symmetry is going to be U, right? So it is actually going to form something like a bigger plus minus big. I can't do justice uh, by the drawing. I should erase. It looks bad. I hope you got the idea how the pi orbital is going to be. MO is molecular orbital is going to be, and it would be sorry, very sorry. It is going to be a Girard symmetry, right? Because plus to minus plus, and there is a heterosymmetric molecular orbital. Okay. With that, we'll go to the next question. The question is, formulate the Hamiltonian for a triangular H3 plus molecular ion equal hydrogen-hydrogen bond lengths. So H3 plus molecular ion, we need to formulate an Hamiltonian. So there are 3 nucleus, 2 electrons, right? Because H3 plus and equal HH distance. So let us first write the Hamiltonian. So Hamiltonian will consist of the kinetic energy of the nucleuses. So there are 3, right? So I can write the summation. I'll start with n equals to 0 to 3 minus, right, minus sign, minus h cut square by 2m n, right, for the nucleus. I'll write it in bigger. summation delta square Laplacian square of your nucleus. There are three nucleus, right? N. Then there is the kinetic energy terms for the electrons, and there are I should INJ, I should write it like that, right? J equals to 0 to 2. I'm writing it very bad. I'm very sorry. It is not 0. It should be 1, right? 1 and 2 it got, then as there are 2 electrons, right? And what else? So these are the kinetic energy terms. Now comes the potential energy terms. In potential energy terms, there could be attractive potential and repulsive potential term. First, let us write the attractive potential uh, things related to the electrons. Okay, first. So as it would be attractive, so I'll start with a minus sign, and then I can write your Q Z. Q is 1 by 4 pi epsilon 0, or you can write it QZ square by, now I'll write 1 by R first electron with A. Suppose there are three nucleus A, B, C. So my first electron will receive a attractive potential energy with with one of the nucleus, that is A nucleus. Similarly, it will have a attractive potential from the B as well as C nucleus. Now I have another electron, that is 2A. For there will be 3 terms, right? Again, so these are my electron nucleus potential terms. What? So I'll also write it at the end. What are the terms? Then I have repulsive terms, right? Between the electrons, that is only one, that is R12. That is repulsive. And I am going to have a repulsion between the electrons, sorry, the nucleuses, right? That would be, I should write R AB, R BC, and 1 by R CA. You can write it in whatever manner. AB and BA are going to be same. So I can write it that, and for convention, I will just write this R to be bigger R, the capital R. Now let me explain what these each are. Just write for the benefit. So this is the kinetic energy terms for nucleus, 3 nucleus. I should write nuclei, right? Or kinetic energy for electrons this part is attractive potential between electrons and nuclei, right? This is the repulsive potential energy between two electrons. That is why. So, and this is the say potential G in the nuclei. Okay. And Z is actually 1 as it is we are taking as hydrogen, right? So I can erase Z. Okay. No big deal. Because the atomic number is going to be 1, right? And this is the first part where we have already formulated the Hamiltonian for the triangular H3 plus molecular ion. Now the first they want us to write the linear combination of atomic orbital expression for the lowest energy MO using the atomic orbitals of hydrogen. Sketch the contour of this MO and show shines. So the first part, that your lowest psi MO, that is actually your lowest psi MO is actually nothing but your one of psi bonding molecular orbital, which is actually I should write 1 by 3 or 1 by root 3 psi 1 plus psi 2 plus psi 3, where your, or I should write psi, I will write it in a different maybe in notation, as these are all hydrogen. I can write 1 is 1 plus 1 is 2 not 2 but 1 is B, 1 is, should not write this manner also. But I am trying to say that you need to take the atomic orbital linear, and as this is the lowest, it should be plus, all plus. So 1 is A, first atom, second C, right, like this. And your lowest energy wave function is going to be actually product of psi BMO monomolecular. So at lowest energy, so H3 2 plus, right? So 2 electrons are there. So psi BMO, 1 electron will be all over this place delocalized, and psi BMO second electron. And you can see so the question is, we have written the LCA expression of the lowest energy using the AOs of the each hydrogen, sketch the contour plot. We need to show the contour plot also of this BMO, of this one. So this is your A, this is your B, this is your C, and as all of them actually are like this. This is the contour diagram. Okay, the sign is actually, the overall sign is going to be plus, right? Because this is plus, 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 plus. Okay, I can write here a big plus, something like this. This is going to be the contour diagram. So the sign we have shown, and we have already shown this. So the next question is, what is the spin wave function of this molecule in the ground state? So in the ground state means the lowest energy state. So the spin, so as you can see that psi, that lowest energy wave function is psi bm1 and psi bm2, so it is actually going to be symmetric, all are positive. So your um, lowest psi spatial is actually symmetric. So accordingly to that, your overall wave function should be antisymmetric. So your psi spin should be antisymmetric, right? And there is only one antisymmetric case, that is alpha 1 beta 2 minus alpha 2 beta 1. Another approach to write this is write the beta first, but okay. So this is your spin wave function is going to look like. Now express the ground state wave function of this molecule in a single Slater determinant. To be honest, that is actually very tough, but with all the multiplication terms, but the easier way would be the Slater determinant. So remember, right, the Slater determinants. So, these are based on this spin orbital. Spin orbital is your total spin, that is psi spatial into psi spin. So here we can write, actually your psi is total is psi bmo1 psi bmo2 into 1 by root 2 into alpha 1 beta 2 minus beta 1 alpha 2. So if you want to write in a Slater determinant, it would look like psi total is psi bmo, and I will keep alpha at the first spin orbital, and I will keep it, the orbital as fixed in the columns, and I will change the orbitals with rows, or I should say in all the rows I am keeping my spin orbitals same. In columns I am changing them, so it is BMO beta. And now I will, so this convention I'll put 1 1 here. Here it will be 2 2. Here it will be 1 1. This is very small. I have made use a different color maybe. I am changing the electrons in rows, keeping them fixed along the rows. Okay, so this is how my spin orbital is going to look like. I should not overwrite. Okay, where alpha beta are up and down spin, or you can say accordingly to your convention. In this convention of the Slater determinants, I have kept my spin orbitals to be same along the rows, and different my electrons I am putting same along the rows. So sorry, I have made the mistake by saying the spin orbitals are same along the column and electrons the same along the rows. Okay, I hope you can see, and you will get if you expand this psi total here, you are going to get this. Okay, with that I guess any other question left? No, for 3 there are no questions left. Now there is a question, interesting question from the MOT. This is a numerical question. This kind of questions actually can come in CSIR or in exams also. The question says that the photoelectron spectrum of a second row homonuclear diatomic molecule. Second row homonuclear diatomic molecule could be N2O2, something like that. Molecule is recorded using 21.21 electron volt of photons. Okay, it is observed that the maximum kinetic energy of the ejected electrons from the top 3 molecular orbitals are given as 10.01, 8.23 and 5.22 electron volts respectively, with a intensity ratio of 1:2:1. Sketch the MO energy diagram and identify the molecule. Okay, firstly I have kept two red things, that second row homonuclear diatomic and intensity ratio of 1:2:1. So second row so there could be two type of MOs for second row atomic dinuclear, right? One up to N2 nitrogen, and another is after nitrogen, that is from oxygen and fluorine. So up to nitrogen from you can say lithium to up to nitrogen, the problem is that there is the gap between 2p and 2s of each atomic orbitals are less, so that sp mixing is there. So we have two cases. In one case, so 1s we don't have to bother about that. So they are going to form sigma 1 star, sigma 1s. Now with 2s there is sigma 2s, sigma star 2s, right? Antibonding. Now there are 3 2p, and I should always write this energy scale to be upwards. You should also make it a habit to show this arrow, energy arrow. I have so this is very important, or your marks can be deducted, as my marks was deducted uh, in my graduation, and from then on I don't forget to keep this arrow, energy. I always show these things as the energy is going upward, right? The energy is increasing as we are talking. Means 1s, 2s, 2p. Now, as there could be two cases. I will again draw the same. So this is up to nitrogen and this is beyond nitrogen. Two cases. Up to sigma 2 star there is not much problem. There is problem will come as up to nitrogen there is sp mixing. So at first whatever in this case at 2p, z's are going to form sigma orbital 2pz 2pz, but in there is much gap in case of beyond nitrogen. So the 2p sigma 2pz and sigma star 2pz should be like this. They can stay like this. Wait, I will not show these connections or it would be very bad looking. And there could be pi, and here would be pi stars. Okay. But in case of up to nitrogen, I should draw these 2s and 2p are really they are close. So I'm keeping them close. Okay. So there is an sp mixing, that is why your pi are going to be here, then your sigma 2pz are going to be here, then again obviously your pi star, and then your sigma star 2pz. You got my point? So this is the difference of molecular orbitals energetics up to nitrogen and beyond nitrogen. As they have mentioned the second row homonuclear diatomic molecule, so the MO diagram could be either of these two. If they have written it is a third row homonuclear diatomic, then you could have directly work with this, and you understand what my point is. Okay, now we have taken care of this thing. Now the molecule is recorded with 21.21 electron volt. So here the photoelectric effect, Einstein's that your H nu upcoming photon, that is equals to energy of that is equals to your some work function, right, plus your kinetic energy of the electrons, right, work function of the metal from where the electron is coming. So this is your work function, right, and this is the energy of photon, that is for the first, and intensity ratio of 1:2:1. So from the top MOs, or you can say top occupied MOs, right? Okay, so let us first see that what are the binding energies of these three type of electrons. So for the first case, kinetic energy. So this is 21.21 electron volt. You can say this is as binding energy also. So the first case is 10.01 eV. So 5 WA for the first, the top. See, the kinetic energy would be high, right? Kinetic energy will be high if your MO is located at height. So it will have a lesser binding energy. So with that, excess energy would be kinetic energy. So kinetic energy would be higher for the topmost molecular orbital. So for this it is something around how much? This is 0.20 eV and it is 11, right? Okay. For the then it is 21.21 eV again is 5 work function for 2 and this was for 1 and now 8.23 eV. So for this binding energy at second is 21.21 minus 8.23, right? That would close to 12.98 eV. What about the third? Third is work function or the binding energy of third set. You can never know that if it is 1 electron, 1 is to 2 is to 1 doesn't really mean the 1 electron is ejected, then from the second is say 2 electrons are ejected and then the lowest 1 electron is ejected. It could be 2 is to 4 is to 2, which is actually 1 is to 2 is to 1. But for first let us calculate this 21.21 minus 5.22 eV. $15.99. Okay. So these are the, so this third electron is buried, second electron is then less buried, and first electron is the topmost MO, what they are trying to say from the photoelectron spectra. So actually in photoelectron spectrum you are actually it will follow the photoelectric effect, right? Okay, so the intensity ratio is now given 1 is to 2 is to 1. So let us see which model fits that up to N2 or beyond N2. See, 1 is to 2 is to 1. From there we will get the idea also that which molecule it is, right? So let us feel. So can it be something like that? This has 2 1 1 single electron and it cannot have sigma star 2pz, either pi star has to be 4 4 2 2. That could be one case, or it could be something like that is one case for this, huh? And up to nitrogen, what is the, for nitrogen what is the MO looks like? Nitrogen is 7 7 14 electrons. So let us put 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Okay, so we have to follow the Hund's rule also. We cannot put 2 here before filling up these pies. And beyond nitrogen there is oxygen. For oxygen it is 16, right? 1 2 3 4 5 6 7 8 9 10 11 12, 13, 14. So these are degenerate. And 14. Now 1 each, one similar spin in pi star. So if that is the case in homonuclear, we try to see. So the sigma star is not filled in case of. So if we go to fluorine also, fluorine is what? Fluorine is 18, two more electron. So we would have filled the pi star. So that is 4. And in case of nitrogen, and this case up to we can go up to this. So as you can see, the intensity ratio is given 1:2:1. It could be either oxygen, it cannot be fluorine, right? And it cannot be neon for sure, because neon Ne2 doesn't really form, right? Homonuclear, because you know why, right? Because the bond order is 0. Then for nitrogen, we can see what is the order. For nitrogen, acha, for nitrogen, the sigma star 2s is deeply buried, so it will require a very high energy, right? 2:4:2. Actually, the situation is like that. But in case of oxygen, see, so these pi electrons have similar energy. So actually, the molecular orbital is actually, if you see from the energetics also, 11.20. This is binding energy is 13, and this is 15.99. So actually your molecules could be nitrogen or oxygen, and we cannot really be sure about which one is it is, right? As you can see, from here you are getting 2 electrons, here 4, now 2, here also you have 2, 4, 2, which is 1:2:1. Here also 1:2:1. So your molecule could be either nitrogen or actually could be oxygen. It could not be fluorine. If you put the electrons, you are not going to get 1:2:1. Or if you go beyond below into, that is carbon C2, then it could be 4:2:2, right? So which is because your sigma 2pz won't be occupied that time for carbon, right? C2. Or below that B2 boron, then your it will be paramagnetic again, right? 1 2 2, so it will be 2 2 2 in case of the boron, because then the top homo would be pi orbital, uh, and pi bonding, so that there will be 2 unpaired electrons, right? So it would be 2:2:2, that is 1:1:1. So if the intensity ratio is given 1:2:1, then there could be two possibilities. Your molecule could be nitrogen or oxygen, and from the experimental value you have to be sure which one it is. I hope the concept is clear. From this concept you can solve what is the energetics. First concept is the photoelectron effect, and the second is what are the how to identify your homonuclear diatomic molecule from here, right? So we'll solve, maybe with the time we have, we can solve another question. uh, Here we have the question says the qualitatively draw bonding and anti-bonding MOs formed due to the overlap of two 2s and 3pz atomic orbital. So 2s orbital, number of 2s orbital is 2 and one 3p z orbital. Assume internuclear axis to be the z axis, z direction, and show nodes and sign of the MOs. So how your 3pz looks like? So there are one radial node, right? So this is, suppose this is the z axis, I am saying this is the z axis. One is plus and minus, but this is 2p, and this is your 3p, right? Minus plus. Suppose I am saying this is my 3p, and how does my 2s looks like? There are one radial node also, right? Suppose I am keeping between plus and the upper one minus, and similar for this plus and minus. See, in the first case, this side is matching, this side is not. So 2s, 2s, and this is the z axis, internuclear, right? So we are actually thinking about the sigma MOs, which are head-ons, not the side-ons. So one could be 2s minus 3p minus 2s. How it would look like? Plus minus. Minus 3p would be minus plus minus plus and minus 2s is okay. See, there is only one node here and radial angular node, and these are all forming a bonding molecular orbital, one case. And another would be the anti-bonding would be 2s plus 3p minus 2s plus minus, now it is plus 3p. So I have already identified my 3pz, I should say, right? So I have already put my convention that my 3pz look like this, not the minus plus plus minus. So that could be another. So it depends on the convention, and that will reflect on this minus or positive signs. Okay, but you don't have to worry about this. Here the exercise is to just to get the idea how to draw the MOs or how to show the overlaps. Minus plus minus. Now this is again minus, plus, and in between there is minus. See, minus plus, there is an node. Here is obviously there is a node, and here is also a node. So this is your anti-bonding molecular orbital. You can also use the wave functions. Let me show you how the wave functions look like, at least for 2s. 2s it would look like this, right? This is it, and it will go. It will be something. Let me use the eraser. Something like this, right? 2s. This is also same. Maximum at the here. Then there is an angular node, a radial node, you can say, does this looks like 3pz. This is that C. Negative, positive, and then again negative. And for this case it is going to be positive and then again. So here it is minus, which I will draw the signs in different color. Minus, plus, minus, plus, minus, plus, minus. So when they overlap, if you see this, you can use that also, right? What I'm trying to say, this is your z-axis, don't forget about that. You can also use that wave function to see how they overlap. See, 2s minus, you have to take minus of these so that they can form a bonding molecular orbital. You can try with these notations and try this. I'll ask you to use these wave functions, right, to see this at your home. Try it yourself. Now actually I have another question. With this question I will stop the session today. So the question is, we have to write the expression of the delocalized sigma bonding MOs of BH2 plus as a linear combination of valence atomic orbitals of appropriate symmetry. Do not invoke sp mixing and consider plus z to be the internuclear axis for this linear molecule. So what are the concepts given that we need to, so these are BH2 is going to be a linear molecule and we need to draw the MO diagram for BH2 plus. So how many electrons there are total in BH2? Beryllium carries 4, 2 of the hydrogen will carry 1 each, so that is total of 6 electron for BH2, and for BH2 plus the total electron is going to be 5. But we don't care about the electrons at first when we are write down the expression for MOs through the linear combination of atomic orbitals. Here the two things are important, that here this is not a homonuclear or diatomic molecule. This is a 3 atoms are there which have different energies, heteronuclear. Obviously beryllium is more electronegative than hydrogen, so beryllium will, the energies, the 1s orbital is deeply buried. So what I'm trying to say, for each, so if this is beryllium and this is hydrogen, so what I'm saying that 1s is deeply buried for this, and for 2 hydrogens there are 2. I'm not going to the Salk, just normal 1s. These are having same energy. Again I should show the energy axis, and energy is increasing upwards. So this is beryllium 1s deeply buried, which has 2 electrons. Then beryllium 2s, which has 2 electrons, and empty 2pz orbitals, 2p orbitals. Out of this, one is 2pz, other two are 2px, 2py, and these are 1s of hydrogens carrying 1 electron each. So firstly, for preparing the MOs and to look at the what linear combination of atomic orbitals we can take, there comes the energy and symmetry matching. So by the energy parameter you can see that 1s is deeply buried, so it will create a non-bonding MO. Okay. Now 2s and 2s is going to participate and 2p is going to participate. How? The 2s of uh, 2s is going to look like this, plus. So let me take minus and plus sign, and your hydrogen two side, one is 1s from hydrogen, beryllium 2s, and plus of hydrogen, this is 1s 1, this is the second H. Okay, so this is going to be one of the molecular orbitals, bonding molecular orbitals, and let us name it sigma G, right? And what could be the anti-bonding? That is plus. So I am denoting this as my plus, plus and minus inside. Now if this is plus, this is minus, this is plus, then there is going to be the node, and this is my, again the Girard symmetry is there, but it is my anti-bonding MO between 1s and 2s of berylliums. Okay, so for this case what I am writing is 1s H11s plus beryllium 2s plus H21s. For this I am writing H11s minus beryllium 2s plus hydrogen, second hydrogen 1s. Okay, so they are going to form a bond something here, which is my sigma G I have said, and they are going to send some sigma G star. Okay, what about 2pz? 2p beryllium looks like plus minus. So one of the cases will be plus and minus from hydrogen. So that would be, if you see, this is an sigma U, and it is formed by H11s plus beryllium 2pz plus no, but minus is another combination, right? And if it is plus, then minus plus, it is going to be sigma U anti-bonding to it, anti-bonding because number of nodes are higher in this case, right? So this is consist of H1s1 minus beryllium 2pz minus H21s. So this is one of the approach, and your px, 2px and 2py are going to be non-bonding of beryllium, I should write, and 2pz forms another, that is sigma u, and one of the anti-bonding, that is sigma u star. So total number of electrons in BH2 plus is 5 electrons. So let us fill that. 2, 4, 5. Okay. Now we have drawn the MOs, we have shown the signs and the nodes, We have assigned the symmetry Gerard or Ungerard. Now the B, question number B says that how many lines or bands are expected in the entire photoelectron spectrum. Photoelectron spectrum means you are putting some energy of photons and then your electrons are ejecting, and based on that you are getting a photoelectron spectrum. So if you see that, then in this case you are going to see the three bands, right? One for sigma u, one for sigma g, one for sigma nb. So three bands, and what are their relative intensity? That would be 1 is to 2 is to 2, right? So binding energy of this is high, then this, and this is very less. Okay, you got it? Got my point? So it would look like this is binding energy, this is 2. Okay, binding energy is increasing, this is increasing intensity. So this is for sigma u, this is for sigma g, this is for non-bonding sigma, you can say non-bonding. Okay, so I hope you understand the problem, how to draw the MOs, how to draw the anti-bonding MOs, right? And how to fill up the electrons then, and what are the type of questions that come from photoelectron spectra. Photoelectron spectra is actually an experimental method to prove the MOs, you can say. I hope with this you will be able to solve the numerical problems. We will meet again on uh, Monday, actually, sorry, on Tuesday. The next Tuesday means the day after tomorrow, to solve some more questions. I'll look, and that would be the final, you can say, week 12 session. And I hope to meet some of you on that day. And with that, I'm stopping today. I hope you have got some idea. Thank you for listening. If you have any doubt, please put up in the comment section, and I will be happy to reply to you.